In this video, I wanted to go over mixed gases review. I believe this is page 30 in your packet. The reason why I wanted to go over this page is because all of the gas laws are going to be mixed in together, and you will have to figure out which gas law or which equation to use for each problem, because it's not going to tell you. There's not that many options. You have what the combined gas law is P1V1 over T1 equals P2V2 over T2. Now we can adjust this for Boyle's law if we need to, which means temperature is not used, or we could adjust it for Charles' law, which means pressure is not used. So it's really giving us three different equations: Boyle's, Charles, and the combined gas law. There is Dalton's law, which is the total pressure is the sum of the partial pressure of all the gases that make it up. So however many that is, you just add them up. You have to make sure they're all in the same units there. And then we have the ideal gas law, which is PV equals nRT, which is the only one that brings into amount, which in this case has to be moles, and this universal gas constant, which we'll get to. So I think the easiest thing to do when you're looking at a problem like this is to figure out what are the variables that are given. So in this, it says if the volume of a gas is 19.4 liters at 4.99 atmospheres. So that's the first volume, and that's the pressure that goes with it. So I'm giving them V1 and P1. It's asking for another volume, so that's V2, and it's giving you a second pressure. But you have to pay attention that these pressures are not in the same units. So what you have to do is convert one of them to the other one. They just have to be the same units. You can either make them both atmospheres or both millimeters of mercury. So for no particular reason, I'm going to convert the 1580 millimeters of mercury to atmospheres. And to do this, you use the standard pressures that were given earlier in the packet. And since you start off with millimeters of mercury, just like when we're doing any conversion, that goes on the bottom because you want those to cancel out. And we are converting it to atmospheres. Now the standard pressure in atmosphere is 1, and for millimeters of mercury is 760. So you do 1580 divided by 760, and that gives you 2.08 atmospheres, and that's what this P2 is. So now what's going on is we're going to take this combined gas law, and we are just going to take out the temperature. So we end up with P1 V1 equals P2 V2. The first pressure is 4.99 atmospheres. The first volume is 19.4 liters. P2 is 2.08 atmospheres, and V2 is what we're solving for. So what I would do on the calculator is multiply 4.99 times 19.4, don't round it off or anything, and then just divide by 2.08 because we want to get this V2 by itself. So essentially what we're doing is this. The atmospheres will cancel out. V2 you should get as 46.5 liters, rounding it off to 3 significant digits because that's what's given in the problem. Now for this, before you even get your answer, you should kind of think about it. And if you see what's going on here is the pressure is going from 4.99 atmospheres down to 2.08 atmospheres. So pressure is decreasing. Pressure and volume have an inverse relationship. So if pressure is decreasing, you should expect the volume to increase, and that's what happens. It goes from 19.4 to 46.5. Remember, you could double check your work on the bottom of the page. And now for the next problem. If a flask contains nitrogen with a partial pressure of 1.22 atmospheres and carbon monoxide with a partial pressure of 87.4 kilopascals. So it's giving us two different gases and two different pressures. It wants to know the total pressure in the flask in atmospheres. So this is going along with Dalton's law. Total pressure is the sum of the individual pressures added up. But what happens for this problem, we have to make sure they are in atmospheres. Now, nitrogen's already in atmospheres, so that's nice and easy. So what we have to do is take this 87.4 kilopascals and convert that to atmospheres. Since you start off with kilopascals, they go on the bottom. Atmospheres goes up top. That's 1 atmosphere is 101.325 kilopascals. When you do that math, kilopascals cancel out, and you'll be left with 0.863 atmospheres. So now the total pressure, you just add these up. You do 1.22 atmospheres plus 0.863 atmospheres. Now what I'm going to do, since I'm adding at this point, you go by the least number of decimal places. This has 2, this has 3, so I'm just going to round it off to 2 decimal places, and you get 2.08 atmospheres. All right, so that's numbers 1 and 2. Number 3, a student drops a piece of zinc into a beaker of hydrochloric acid and collects the hydrogen produced in a balloon. The volume of the balloon is determined to be 812 milliliters. The temperature of the room was measured to be 21 degrees Celsius. So that's giving us V1 and T1, but I have to make note that's in degrees Celsius. We'll have to convert that. What volume would this hydrogen balloon occupy at standard temperature? So it's asking us for V2, and T2 is standard temperature. All right, so now if we were going to look back at the combined gas, so that P1 V1 over T1 equals P2 V2 over T2, we could use that. We just take out the pressures because pressure is not listed here anywhere. But I want to pay attention to this. This 21 degrees Celsius, we have to convert that to Kelvin. So you add 273 to it, and that gives you 294 Kelvin. T2 standard temperature is 273 Kelvin. So what we could do is V1 over T1 equals V2 over T2. Sometimes people like to cross multiply and have V1 times T2 equals V2 times T1. You could do that if you want. Pick whatever way works best for you. But I'm going to start plugging these in. Now the other thing, well, now we're good now. So 812 milliliters is V1. T1 was this 294 Kelvin. We're solving for V2. T2 is standard temperature, which is 273 Kelvin. For me, if I was doing this problem, what I would do is get the answer to this side first, because I have all the variables on the left. I would do 812 divided by 294. And then while that answer is still in the calculator, just hit times 273. And that's going to give you your answer. V2 ends up being 754 milliliters. I know it's milliliters because those are the units for volume given in the problem. The Kelvin will cancel out. I rounded off to 3 significant digits because that's what's given in the problem. Now for this, if you notice what happens here, the temperature decreased. And volume and temperature have a direct relationship. So if the temperature decreased, I should expect the volume to decrease, and that's what happened. It went from 812 down to 754. All right, number 4. A gas occupies 72.0 milliliters at 25 degrees Celsius when 198 kilopascals. What is the volume of the gas? All right, so now it's giving me other information here. So I have V1, T1, and P1. Again, this is degrees Celsius, so I have to watch out for that. It's asking us for V2, it's giving us T2 and P2. So now this is where I need everything. P1 V1 over T1 equals P2 V2 over T2. I have to pay attention that this is in degrees Celsius and this is in degrees Celsius, so I'm going to have to convert those. The pressures are in the same units, so that's good. So 25 degrees Celsius, you add 273 to that, and that gives you 298 Kelvin. 45 degrees Celsius would end up being 318 Kelvin. So now I can plug all this information in. I have 198 kilopascals for P1. For V1, I have 72.0 milliliters. And for T1, I have 298 Kelvin. For P2, I have 129 kilopascals. I'm solving for V2, and T2 is 318 Kelvin. So now what I would do on the calculator, again, since I have all the variables on the left, I would get this answer first. 198 times 72 divided by 298. Get an answer on the calculator. Then multiply by 318 and divide by 129 kilopascals, and that's going to give you your V2 of 118 milliliters. All right, so that was problem number 4. Problem number 5. This one looks a little different because it's giving us an amount. It's giving us grams. And it's giving us volume and only one temperature. So that's telling me I'm going to need the ideal gas law because amount came into it. And that's what this N is, except I need that to be moles. There's only one pressure. No, it's asking pressure. I'm sorry. There's only one volume and one temperature listed. But I have to pay attention to some units here because I'm working with R, and R is 0.0821 liters atmospheres per mole K. So I need to make sure I have these units. So I have to convert this to liters, I have to convert that to moles, and I have to convert that to Kelvin. So first thing I'm going to do is figure out moles here. 2.94 grams of C2H8. You put grams on the bottom because we want that to cancel out. You get the numbers off the periodic table. That should be an 8. You have 2 carbons, they're 24 apiece, or 12 apiece, I'm sorry. 2 of them gives you 24. Add another 8 to it, that gives you 32.0 grams, and that is what's in 1 mole. So that gives you 0.0919 moles. 83.2 milliliters, that's pretty easy. You just move the decimal point 3 places to the left. 0.0832 liters. Negative 24 degrees Celsius. You add 273 to that, and that gives you 249 Kelvin. So now when I plug this into the equation, well, I want to solve for pressure. So what I want to do is divide both sides by volume to get that pressure by itself on the left. So I'm going to have pressure equals this mole, 0.0919 moles. I'm going to have R, which is 0.0821 liters atmospheres per mole K. And it helps when you write the units in these problems because it'll let you know if you're setting it up right or not. So I always take the time to do that. I think it's worth doing it like that. And the volume is 0.0832 liters. So now when I do this, the moles will cancel out, Kelvin will cancel out, liters will cancel out. What I'm left with is going to be atmospheres. So on your calculator, what you should get when you do that is 22.6 atmospheres. All right, now number 6, it's giving me a volume. If 711.2 milliliters has a pressure of 1.89, so that's the pressure and the volume that go together. It's asking for P2, and it's giving you V2. So this is going to be another Boyle's law. You can start off with the combined gas law, take out the temperature, and this is what you end up getting. The volume is not in the right units. It doesn't specify what unit for pressure, so I'm just going to leave it in atmospheres. So what you end up doing is 1.89 atmospheres. Now I'm just going to leave it in milliliters. You could convert them both to liters. It doesn't matter. They just have to be the same units. And this is why you want to write the units in the problem. We're solving for P2. Now V2, I'm just going to make this into milliliters, so it ends up being 1,440 milliliters. Multiply this side, get an answer. Divide by 1,440 milliliters, and P2 will end up being 0.933 atmospheres. All right, so when you're doing these problems, make sure you label the units that you're given, right? Because that'll help you figure out what problem to do. Now, there's another one I wanted to do that's not in the packet. And I'm running out of time here, so I think I'm just going to end up doing this on a different video.